In this lesson, we're going to take a look at how atomic theory has changed from when Dalton first proposed it until the early part of the 1900s. We might later take a look at the more modern model of the atom, but this one will get us started for our basic introductory to chemistry. So first we have to realize that Dalton's atomic theory worked until it didn't. It was a good idea, but then some experiments started coming along that showed that it wasn't quite complete. And a major one that helped us understand that was work that John Dalton did. He was an English chemist with the cathode ray tube. So a cathode ray tube is a fairly straightforward device. It's this empty glass tube, and then you put it under vacuum, so you suck most of the air out of it. So when I say it's a rarefied gas, it's a low pressure gas in here. Then this plate is called the cathode. It gets a negative charge. This plate's the anode, gets a positive charge, and that's a very high voltage source that provides that. And what happens here is particles accelerate off of this metal plate towards this metal plate. But there is a hole in this plate that allows a single beam of those charged particles to come through. And these charged particles, you can see them, they glow, nice green beam. And if you don't apply any field, there's magnets and electric fields here, to this charge, to this beam, then it just flies straight through. That's this dashed line. But if you start applying a magnetic field or a charge to it, then you can deflect this beam. Now, Thomson did a lot of different experiments. He changed the amount of air in there, and that had some effect on it. You get no air in there, it doesn't work. Too much air in there, it doesn't work. But rarefied air, pretty high vacuum, it works okay. But changing the metal, where the charged particles come from and where they head towards, has absolutely no effect on what's going on in here. And so what Thomson concluded from this was that there is a particle that's emitted from the metal that you can deflect with a charge, which means that particle is itself charged. And by using magnets and charge plates to deflect this, he was able to calculate how much force it took to deflect these things based on their charge. So he was able to do a charge to mass ratio of this particle that was coming through. And because it didn't matter what metal he used to create these things, he said there's a couple things that we can conclude from this. There must be a negatively charged piece. He knows it's negative because of how it reacts to the fields. And it must not matter what kind of thing it comes from. So all elements, all atoms, contain these negative pieces. He also realized that they're much smaller than atoms themselves. Now, Thomson thought that perhaps these electrons, he didn't call them that, he called them corpuscles, were all together in a cloud within the atom, or maybe stuck throughout the atom. He had his plum pudding model, but he was the one who showed pretty conclusively that no, atoms have to be divisible because there's this smaller piece that is common to all atoms. So an electron is an electron, doesn't matter what atom it comes from. Now, Millikan kind of refined this a little bit, because what Robert Millikan was able to do was actually figure out how much charge an electron had. So this diagram down here shows Millikan's oil drop experiment, and basically what he did was he sprayed in some droplets of oil and charged them by shooting x-rays at them. And then these oil drops would fall because of gravity, but he would turn on an electric field, voltage between the positive and the negative plates, and he would catch those falling particles, and he could measure how much electric field it took to hold them up, which allowed him to calculate the charge on each one of those oil drops. Now that in itself isn't all that spectacular, but he did this enough times with enough different drops that he got lots and lots of different data, how much different charge it would take to hold these different drops. And because each drop has a random amount of charge on it, depending on how much X-rays it absorbed, he was able to calculate the least common factor of that charge, and he said, well, that must be the fundamental. That must be the step that we can take between. That must be the charge of an electron, because the charge is coming from the electron. And so he was actually able to measure the charge on the electron, which allowed the mass of the electron to be calculated, which is this tiny little number here, times 10 to the negative 37th kilograms. So Millikan was able to show that these things are indeed really, really small. This is just kind of a summary of what we've learned up until this point. So it used to be that we had John Dalton's atoms, which were just solid little spheres that could hook together. Now we've got Thomson's model, which shows negative particles that are scattered throughout a positive cloud. And so that's over here. There was another scientist who proposed, well, maybe it's more like Saturn, where you got a positive center and an electron ring around it. But 1903, 1904, these were also then showed to be not quite correct. And in fact, it's kind of interesting that they were showed to be untenable by a student of J.J. Thomson. So Ernst Rutherford was a New Zealand scientist, although he did a lot of his work in England, and he is credited with the gold foil experiment. He liked to experiment with radioactive element, radium. Radium produces a stream of alpha particles. Now we know today that an alpha particle is 2 protons and 2 neutrons. It's a helium nucleus, but he didn't know that. He knew they were positive charged. He knew they moved really, really fast. So what he did was he took a very, very thin layer, a thin foil of gold, and he shot these alpha particles at them. And what he noticed was most of the alpha particles went straight through. That's what this shows. A few of them were slightly deflected, and an even fewer amount of them bounced almost straight back to where they were. Now, what that means is atoms are mostly empty space because these alpha particles can go through unimpeded. But because some of them are deflected and some of them are bounced completely back, that deflection is probably caused by 2 positive charges getting close to each other, pushing on each other, and that causes that deflection. And same with bouncing back. But because so few of them bounce back, that positive charge has got to be concentrated in just one spot. And so Rutherford proposed the idea that, no, it's not a cloud of positive in the middle. It's actually a very, very tiny dense place in the middle where all that positive charge is located. He called that place the nucleus. His further experiments showed that that nucleus is positive due to a positive particle called a proton. In fact, he was able to determine that the nucleus of a hydrogen atom is a single proton. But again, there's going to be some issues here because just having the nucleus does not explain everything that we can get out of experimentation. So this is sort of an in-close view on Rutherford's gold foil experiment. You can see alpha particles are coming through. That's the green rays. Most of them are going through the gold atom here, and you can see where they just go through the gold circle part. They mostly go through unaffected. When they get too close to particle in the middle, the nucleus, they deflect or bounce back, and that's because the gold cloud actually here is mostly empty space because the tiny little electrons, remember this is not anywhere close to scale, electrons are way, way small, are flying around out here in this space, and the nucleus is in the middle. So Rutherford proposed sort of this model of the atom where you have electrons zipping around in orbits around the dense nucleus. But this doesn't explain some other things. So radioactive decay was kind of a newish thing in the early 1900s, and we were doing a lot of experiments with these. And what scientists could find was that in the case of decay, atoms of one element would change into atoms of a different element, which doesn't happen in chemical reactions, but in radioactive decay you have nuclear things changing. And they would collect a bunch of these different elements that had atoms of slightly different masses, and that's how they knew they had different elements. But then once you had groups of these and you started analyzing them, these different elements actually turned out to have identical chemical properties. And so that meant that something weird was going on, because if they have identical chemical properties, they're probably the same element, but they have different masses, so something was conflicting with Dalton's original theory that said atoms of the same element have a characteristic mass. So Friedrich Soddy proposed the idea that, you know what, we can have different masses of elements, or of atoms that are actually the same element. And he called those things isotopes. And in 1932, about 10 years later, James Chadwick was able to explain how isotopes came into existence. It's because there's a second particle in the nucleus called the neutron, and the number of neutrons within a given element's atom can vary without changing the chemical properties. So neutrons in the nucleus, together with the protons, is what gives most of the atom's mass. Electrons zip around the outside, and we can actually change the number of neutrons inside the nucleus without changing what element we have. The same is not true of protons. The number of protons does in fact determine which element is present.